So it's my pleasure to introduce Katie Antypas. She's the Services Department Head at NERSC, the National Energy Research Science Computing Center at Lawrence Berkeley National Laboratory. As Services Department Head, Katie has oversight of the Advanced Technologies, Data and Analytics Services, and the User Services Groups. Katie is also the project lead for the NERSC 8 system procurement, a project to deploy NERSC's next generation system in the 2016 timeframe. Maybe she'll say something about that today too. From 2010 to 2013, Katie was the group leader for user services at NERSC, a team of consultants who work directly with scientists to help them use the NERSC resources effectively. So you probably, if you've run on NERSC or interacted with their staff, been working with people that have worked with or under Katie. So let's welcome Katie. It's morning. Let's give her some applause.
Hello, is that on? Well, thank you for having me. I hope we're all have our granola bars and are ready to get started here. I will definitely not talk at you for an hour. I don't have that many slides, and I hope to ask you questions and have this more as a discussion. So I guess my first question is, since I'm from NERSC, how many people are NERSC users? Oh, great. Okay. And if you're not a NERSC user, have you run on a supercomputer at Los Alamos, Argonne, Oak Ridge? Okay. Yes, and probably that's good. And then also remind me, the CSGF fellows, you guys are all, is it domain scientists first, and then and also computational science, or is anyone in a pure CS track who's a fellow? There can be some.
Mainstream CS students for whom the application is there.
Is the thing. Okay. All right. Great. So the title of the talk is Preparing Your Application for Advanced Manycore Architectures. And so I thought the first thing we should define or understand is what is Manycore. I think the first time I was reading a proposal and it had Manycore all over the place, I thought it was wrong, and I just, been very confident. I just corrected them. I just changed all of Manycore back to Multicore, because I thought, who would put these two words together? It sounded really silly. It sounded really silly to me. And then I sent it back. It was like Eric Strohmeyer, and he's like, no, it really is Manycore, Katie. I said, oh, sorry. So I guess there's no precise definition. What changes from multi-core to many-core? Something you can say is a many-core, there's many lightweight cores. What does lightweight mean to you as a programmer? It means slow, right? That's what you're faced with, is many slow processing cores. And one way you can think about it is with a many-core architecture, maybe the number of cores is more important than the speed of any given core, whereas maybe in the multi-core era, you're still thinking more about single core and single thread performance. In terms of numbers, it's approximately an order of magnitude, I think maybe a half order of magnitude different between what we're calling the multi-core era and the many-core era. So that's where this weird name comes from. I don't really know who defined it, but we're now using it all over the place. Okay, so then in this next chart, it starts here on the x-axis here is time. It starts here. I was born around here. Now this group, you guys are probably born around here, somewhere in the late 80s. So what this is a graph of is the increase in processor performance over time compared to this VAX system, which none of us, except for maybe a couple in the back, have programmed. And so what you see is, like, during the 90s, during your childhood, folks weren't having to really change their software, their applications, in order to get better performance, right? The computers, they ratcheted up the clock speed. You didn't have to do much to your software, and you were just happy. You got these gains. Then in the early 2000s, it sort of started to curve a little bit, but we still didn't change our software, because that's really hard. So we're still hoping that the computer vendors will help us out and make these faster processors. And now you get to this point where your clock speed and your single thread performance isn't even increasing, it might even be decreasing. And so the question is, why is this happening? And so there's a couple, we call them walls that you run into, and one is the power wall. And the best way I can explain the power wall is, as you turn up the clock frequency, the power is proportional to the voltage squared, right? So as you're turning up that clock frequency, the power that is being used is more than the extra performance that you can get out. So these designers looked and said, actually, I can get more performance if I say 2 cores, use 2 slower cores than using 1 faster. And then they said, well, if I can do 2, then I can do 4. If I can do 4, I can do 8. And all of a sudden, you're out at Manycore. The other challenge that we're running into is what's called this memory wall. And the way I explain this is memory speeds aren't increasing as fast as compute, right? So if you had all the data to the registers, they could compute plenty fast. But the problem is getting that data out of memory. So it's like if I'm eating, I can eat very quickly, but the pipeline to me is just very narrow. And so these are, but all I can eat here this morning is this granola bar. So I'll have to go down and find, that's a very narrow pipeline. Okay, so I think people have seen this graph so many times, but I think people go through it too fast sometimes. Okay, so what does this mean for you as users? Well, it actually means your job is harder, that you're going to have to program for these many-core architectures. So I thought we'd take a look at some sources of parallelism that are both new and old. Okay, so why don't we walk through a couple of types of parallelism that you might find in applications. And so this top one, we call it domain parallelism. This is, a lot of this is from the classic Patterson and Hennessy textbook that you guys might have, architecture textbook that you might know. So domain parallelism, I think of this as breaking up your application into tasks. And people are using MPI right now to do that. Now, my associate lab director would tell me I should use a PGAS language. But still what we see at NERSC is that the dominant programming model that people use is MPI. So you've broken up your domain into different MPI tasks that run on processors. Is everyone programmed in MPI here? Okay. So then the second way you may find parallelism in your application is you may choose to add threading within or from an MPI task. And the most common method we see there is using OpenMP. So you might have 1 or 2 MPI tasks on a processor, and you might use OpenMP within a node. And so then the question is, let's see if this is really the advanced session. Why do you have to use OpenMP here? Could you just use more MPI? What's the answer to that? Can you just use MPI everywhere? Yeah. So what? So say more.
I mean, so the idea between MPI is like you can't. The assumption is that every core has its own memory space. The memory spaces don't overlap.
Right.
So with OpenMP, you're like, okay, working on one node shares the memory space, and you don't have to do the funny message passing within the node.
Right. Okay. So you could use MPI everywhere, and often, majority of our users still do. I think we looked at wall clock hours. About 80% of users are still doing MPI only everywhere. And we'll talk about this in a little more detail later, where you may want to add OpenMP. Some people say, well, I added OpenMP and the performance didn't go up. And that, I'm not sure we've ever seen performance go up. What we do see is memory usage go down. Because as this guy over here said, then each task no longer needs its own memory space. So we find in these Manycore architectures that sometimes you actually have to use OpenMP even to fit your problem on the node. But I mean, if MPI everywhere works, most users won't change it until it breaks. Okay, so then the next level of parallelism is something we call data parallelism, or you might also call vectorization. And so it's another form of on-node parallelism. And I know the folks that were programming before we were born all know this. But when I really started doing parallel programming, I didn't think that much about vectors. I'll put my arm up and say that. And that's because the vector, it was these new, the newer architectures. We had transitioned from vector architectures back to just this distributed computing model. But vectorization is becoming really important again. And so what we'll look at is how you can take this loop and the compiler, if you have a longer vector unit, can compute many of these elements at once. And then finally, I'll talk a little bit about instruction-level parallelism. Instruction-level parallelism is something that the computer or your processor handles. And what it will do is it will look through your program and it will try to do something kind of smart. And so if you look at this example here, this is saying I'm going to add what's in register 1, register 2, put it in register 3. And now I'm going to multiply what's in register 0 by register 1 and put it in register 0. And these two are not dependent on each other. So if the processor has the capabilities, which could be either hardware or software, we won't go into that, this can be done in parallel. Okay, so here's the different levels of parallelism that could be in your code. And the challenge for you as a programmer is, okay, so this one, you can't do that much about. Either the hardware and software capabilities are there, and your application has dependencies or it doesn't. So this has been there for a long time, and you can't do that much about it. The top one, well, you've been dealing in MPI for a long time already, so there's not a big change there. But these two in the middle are things that you're going to have to think more about when it comes to advanced architecture. So you're probably going to have to add more thread parallelism. And while the compilers can help you with vectorization and getting more data parallelism, you can help by either giving hints or structuring your code in a way that makes it easier. Okay, and so then on a note here, let's look at two different architectures. On the left is the Intel Ivy Bridge processor, and if you run at NERSC, this is the processor used on our Edison system. Okay, and then over on the right, I have an Intel Xeon-Phi, which this is the Knight's Corner. Actually, Knight's Landing isn't that different. And so what you can see is that there's a significant increase in thread-level parallelism, right? There on Ivy Bridge, there's 12 cores and 2 hardware threads or hyperthreads. And over here, there's 240 cores. So that's a significant increase. And then your vector width is increasing by a factor of 2 as well. Okay, so then the question is, well, why are we doing all this? Why are we going to force you guys to change your applications? Because this is really hard, and it's not just NERSC that is doing this. You've seen GPUs on Titan at Oak Ridge. You've seen, let's see, the Blue Gene architecture at Livermore and at Argonne, and they haven't announced their next procurement yet, but. All of these new architectures are moving in this direction. And so, the question is, why are we making you do that? And I can tell you, as someone who sits on procurement team, there's a very stark, choice. We can choose, let me go back. We can choose to get you a fast processor that has better single thread performance. We can choose that, but what it is we get a lot fewer nodes in that bid. And then our power we pay more for power if we choose one of these architectures that isn't more energy efficient. So I guess that's a good question. Does anyone know, if you run on Hopper, Edison, how much power does one of these supercomputers take? Anyone want to guess? Say it?
1,000 megawatts.
I think Titan's probably around a little less than that, but you're in megawatts, so you're in the right category. I think on NERSC, our biggest one is about 3. I think Titan might be 8. I'm not sure. I'm sure, but you're around the right area. So that's a lot. So let's take a NERSC, since I'm from NERSC. So around 3 megawatts. And does anyone know how much of our budget goes to powering a computer per year? You can think of your own power bill. I guess we buy in bulk, we get a little discount, but how much does it cost us for if you had one supercomputer at 3 megawatts? Yeah, the rule of thumb, it's about $1 million per megawatt year. So you can imagine, as if we aren't very careful with our budgets, which aren't going up, right? We know we're eating granola bars for breakfast. Then, then we have to be very, think a lot about how much we're spending on the operational costs for these systems.
Do you know if NERSC has variable rate pricing?
No, we get I think a WAPA power from the Berkeley lab. I think all these labs have some deal. But we always do say we have very energy efficient power from PG&E, a lot of wind. Okay, so now why don't I talk about NERSC's next supercomputer, which is named Cori. And so here it is in a little summary. If you want to know more about Cori, we've got a lot of information on our website. And if you're a NERSC user, maybe you've actually heard a little bit about this already before. So it's a Cray system. Cray won the bid. And we're going to have over 9,000 of these Knights Landing processors. So Knights Landing, and I'll talk about next, is the next generation Xeon-Phi architecture after Knights Corner. We'll also have some Haswell nodes on there as well. It will use a Lustre file system, 28 petabytes of disk, close to a half a terabyte of I/O bandwidth. In addition, and you'll see this coming out of on I think a lot of supercomputers, is a layer of flash memory that will be used to accelerate I/O. So that's something new that will be coming with Cori. We've negotiated significant support from both Intel and Cray to help users transition these applications to the Knights Landing architecture, and we're looking for delivery in the middle of 2016. And we're going to a new building. So right now we're in downtown Oakland, which is a great spot, but it's going to be good to be back up on the hill, the main campus. Anyone know who Gertie Cori is? First American woman to receive a Nobel Prize in Science, biochemistry. Okay, so this is more on the Intel Knights Landing processor. This slide is very has been approved by Intel, but they're getting much better at releasing information. I said, I can't prepare any users to run on your architecture if I can't tell them anything about it. So we're looking at, it's about 3 teraflops of peak performance. Peak doesn't mean very, very much. So that's not a very helpful statistic. It's a self-hosted processor. Okay, it's not an accelerator. And I think this is something that is going to be very good for users, is that you already have a lot to worry about with finding more threading, parallelism, and data parallelism that you don't have to worry about offloading to a coprocessor. There's greater than 60 cores per processor. There's 4 hardware threads each. That's where we got 240. It's greater than that, actually, so we don't know the exact yield that will come out of this processor. The vector width for double precision will be 8 double precision variables that can be computed at once. The single thread performance is a lot better than Knights Corner. So if you run at Knights Corner and thought, oh gosh, this is really slow, it should be a lot better. And then this is a key feature that there's on-package high bandwidth memory. And the capacity that NERSC is getting, we're getting 16 gigabyte capacity here. Okay. Yeah.
So does this unpackaged memory mean that it's going to be on the socket, and then you can also have normal DDR on socket?
Right. So let's go to this one here. So what this is the real interesting feature, and it'll be very interesting to see how people use it. We don't have the hardware yet. So there is, memory on the package as well as DDR regular DRAM memory. And what we know is, or Intel has allowed us to say, is this is about 5 times faster than this. If you probably know roughly what DDR memory speeds are, then you can say that's pretty fast. That's a significant increase in performance. Now the challenge here. It's only bandwidth. The latency is not better than DDR4. And so that comes, you might think about how that's going to be programmed if the latency is actually the same. Now the key is there's only 16 gigabytes of memory, whereas here, there's, I don't know if I can say that yet, but it's closer to 100, right? So how are you gonna choose, what goes into this fast memory or not? Well, Intel has made a couple different modes that you can use this on-package memory. One is you can ignore it. They say if you don't want to deal with it, you can ignore it and we can use it as a cache. But then your point is, if it's a cache but it doesn't have any faster, improved latency, how much is that going to help you, right? Well, at least you have more space. You have 16 gigabytes more space. So that's a question, and you can see like the CS papers that are going to come out looking at this architecture. The other is they call it a flat model, which basically means you can program it explicitly. You can choose what to allocate, and I think it's basically high memory allocate is the statement that their compilers will support. Or you can do some combination of the two. So this is a new feature and something that will be very interesting going forward to see how people use it and see what increase in performance people see from using it. Okay, so here are the programming model considerations. You can retain the MPI plus OpenMP programming model. You can run an MPI only on it. Many users, if they aren't using a lot of memory, may be able to stay with MPI only. And then there's a question here on how to use the on-package memory optimally here. All right, so now I thought I would walk through a case study. So this is work done by Chris Daly, who's in our advanced technology group, and it's on the Flash code. So we just at Berkeley just keeps taking people from the Flash Center at the University of Chicago and Argonne and recruiting them to Berkeley. And so I used to work at the Flash Center as well, so I'm familiar with this code, but I've been gone for a number of years now. So in order to mimic the Knights Landing architecture, we have a Knights Corner testbed. Has anyone run on Babbage or a Knights Corner testbed? No? Okay. So the Knights Corner testbed basically has these Xeon-Phi in their coprocessors. But what you can do is you can ignore the coprocessor, basically, and ignore the host and run in a single node mode and run as if it was a Knights Landing. Now, it's a different processor. There's a number of different changes. But at least the programming model you can run in that fashion. So Chris was doing a single node case on this Knights Corner architecture. And so what do we know? It's similar number of cores, 8 hardware threads per core, but this coprocessor right now only has 8 gigabytes of memory. All right, so let's see what we get. So he's taking a simple astrophysics application, which is a shock problem, a spherical shock problem, which is called the Sadov explosion. Flash has an adaptive mesh. He's doing something very simple with just a uniform grid. So the parallelization that's used, that they have MPI as well as OpenMP in this code. I think that's all we probably need to know from this slide. Okay, so let's look at the results here. So he's running on one Xeon-Phi here, and then we're comparing it. You know, you got to be fair in your comparisons. One Sandy Bridge isn't a fair comparison. You got to look at two, because we know that the Knight's Landing architecture is a single socket node, and so it's really cheating if you compare it to one Sandy Bridge, because you'll get two Sandy Bridges on a node. Now, I don't know price, but anyway, either way you look at it, this doesn't look very good for the Xeon-Phi, here at all. So in his little test case, and this is the best case performance, he's getting about 17 seconds, and then just using two Sandy Bridges, which is the host node, he's got like almost 3 times faster. So his job was to investigate and say, what is going on? Okay, so the first thing that he did, and something we're having all of our folks on the app readiness team do, is to do a parameter sweep looking at OpenMP threads and MPI tasks. So I'm going to walk through this slowly, because I have a pet peeve when people go through graphs too quickly and I don't understand. So each one of these lines here is holding the number of OpenMP and MPI tasks and OpenMP threads constant, okay? So if you look at the purple one here, this is MPI times OpenMP equals 60. And so in this case, there's 60 MPI ranks, and there's no OpenMP threads, okay? And then go here, there's 30 MPI ranks and 2 OpenMP threads each. So 30 times 2 is 60, okay? And so there's a line for constant 60 way, there's a line for constant 120 way, which is the red, 180 and 240. Does that make sense? Okay, so you guys are faster than I am. Every time I present this, I have to do that. So you can look at the best performance that Chris got was using about, right down here, was using about 15 MPI ranks. And let's see, what is that? Is that 8? It's 8 OpenMP threads. And so that's our number, that's our 17. That was the 17 over here. So that's the best case. That's not even the worst, right? The worst case is really, would be very bad up here. So he's run this parameter sweep, and he says, okay, this is my best area down here. So the next thing he says is, well, maybe it's my OpenMP implementation that's really bad, right? What's causing this to be really not look so good on the Xeon-Phi? So he says, okay, I'm going to go look at my OpenMP implementation. Maybe that's what's screwing all this up. And so he looks, and now he's running one MPI task, and he's just increasing the threads to see how bad is my OpenMP implementation. If it's perfect, as I add an OpenMP thread, my performance should go up. If I add 5 threads, it should go up. Speed up should be 5 times. So he's doing okay here, but now, you know, he gets out to about, what do we say, around 10 OpenMP threads, and he's about 74% efficient. So is this a good OpenMP implementation or a bad? Well, I don't know. 74 is not maybe that bad. I guess out here he's getting to around 50 or 60%. But so he was running right here, 10 OpenMP threads, right down here. So it's not perfect, but that doesn't seem to be the cause of the problem here. It doesn't seem to be the cause of this 3x factor. Okay, so then the next thing, so then this is a reminder about vectorization, is that when the compiler sees a statement like this, it can unroll that, right? And if if your vector width is 4, it can actually unroll this loop 4 times. And in the perfect case, you should see a speedup of 4 if you were just measuring that loop. Okay. So what did Chris look at here? So Chris turned on and off vectorization. Let's look at, so the red is no vec, that means there's no vectorization. The blue is vectorization, and there's basically no difference here. In some cases, the vectorization is actually worse. So this application, Flash, which is, you'd think would really benefit from some vectorization, is not getting any benefit at all. And so what Chris looked at is, like, let me look back at this data structure. And if you look at the Flash data structure, there's an array of structures. And so for every point, every grid cell, there's a data point on density, pressure, temperature, x velocity, y velocity, z velocity. And then you go to the next point, which is density, pressure, temperature, x velocity, y velocity, z velocity. And so that is very hard for the compiler. The compiler doesn't know what to do with this. It doesn't know how to vectorize that. And so basically no vectorization is happening at all. So what Chris did is he said, instead of having an array of structures where I have density, pressure, temperature, x, y, z, velocity, he said, let me get an array of density. Let me get an array of pressure, have an array of temperature. And this is much simpler for the compiler to vectorize. So he took a little kernel out of this huge, massive code. And so he basically did this inversion. Instead of having an array of structures, he had, I guess, a structure of arrays, or he had multiple arrays. And so now let's look at the results when he did that. So the baseline here is blue, and then the baseline for with vectorization is in purple. And so this is the one where there's basically no difference. And he also ran on the Ivy Bridge processor, and he also ran it on the IBM Blue Gene too. Okay, so now in the new case is where he's flipped the data structures. That's red. He already sees an improvement without even turning on vectorization. So why would that happen? It didn't happen there, but why is it happening? Why could it be happening here? He's not even turning on vectorization. He's getting better performance. Yeah, so you're just laying things out better in memory, so it's probably having higher cache reuse. And then he turns on vectorization, and on the Xeon-Phi sees a big speed up here. So basically, with these optimizations, I think he runs about even with the Sandy Bridge.
Why Blue Gene Key?
He didn't look into this. He wasn't able actually to figure out this out, why it actually went down a little bit here. I mean, you can see with vectorization, it went back up, but he was still exploring that. Yeah.
I'm going to guess back and say the cache structure
Is different.
Hit cache worse.
He might have hit cache worse there on Blue Gene. Yeah. But then once you tell it to vectorize, then it's back up there. Mm-hmm.
You say that it does better than the Phi. Is that with respect to still the old way of doing things on the Ivy Bridge, or is that now with respect to the new way?
Yeah. So I think actually, what did that? Yeah, so this was the baseline when he didn't have the vectorization on at all. And so he's basically getting a 3 times performance improvement. And the difference back here was about 2.9. So I think he's running about even. I mean, what we know is that the Knight's Corner architecture is not a great proxy for Knight's Landing. And so we're looking for 3x the single thread performance and some significant improvements in the processor. So that's what at least that's what they tell us, right? So.
The Xeon
Yeah, actually, so that's correct. Is what we find is if you're right. So now you're right. Now if you'd be worse off. But this is an interesting finding. I know they found it at Titan and at Argonne as well. Is once you prepare your code for one of these advanced architectures and you run it back on, just an x86 or an Ivy Bridge or Sandy Bridge processor, you see significant improvements. Mm-hmm.
Do you know how many fields were in this calculation and what the most fields that a particular update depended on was?
A field, so like I think it was probably the standard like 9 to 12 variables that I've been away from the Flash code a little bit, but it's usually density, temperature, pressure, X, Y, Z, position, and space. So it's usually the base was around 10 or 12. And I think he was just doing the simple case. Okay, so then the results or the takeaway from this is that you really need to look at your OpenMP and MPI efficiency. You need to find where you're running most optimally. Vectorization does matter, and you have to make sure that your data structures are such that the compiler can do the right thing. I mean, what Chris did is, he showed this big improvement. I think the story that's not there is Flash is a massive code. And he just changed the data structure in this one kernel. But if you had to change that for the entire code, that's a lot of work. And so we're very aware of that, not trying to undersell how challenging this will be. Okay, and yeah, again, changes that were made to the code benefited or improved performance on a number of different architectures. Okay, and so I think this was, I think I went over this too. And we had a number of people do case studies on our application readiness team. And one of the takeaways too was some people couldn't even fit their problem in memory on the Knight's Corner card without using OpenMP. So a lot of people just had to add it in order to even run successfully. Okay, so now I was going to transition to preparing, your code for Manycore architectures. Let's see, how am I doing on time? Am I okay? Okay, so our job at NERSC is to help domain scientists get higher application performance. And so we know not everyone is going to become a performance and architecture expert. So we've tried to put together, somewhat of a step-by-step plan on how you can improve your code without overwhelming you with, doing another PhD in architecture and performance. Okay, so these are the stairs that you will have to climb to get better performance on one of these architectures. And so the first, I think it goes without saying, is that you need to profile your application. It's sort of surprising how many NERSC users don't do this, right? And so you first of all, you have to know where your code is spending the most time. You guys are the CSGF people, you know this, but if this is your distribution of how your wall clock time is divided up, it doesn't make a lot of sense to at least start with something that's not taking very much time. It's worth repeating because I think a lot of people don't know where the most time is spent in their codes. Okay, the second is you need to find out how much memory your code is using. Okay, it's important to know what's the high watermark, how much memory am I going to use so you know if you can fit on the processor. It also helps in this case you're showing something's not load balanced correctly. So that, and we get a lot of jobs that crash because people run a node out of memory, whether they did it on purpose or not. Okay, and then the last is you should understand which MPI routines are taking the most time. Make sure you can reduce communication and that you don't have aren't spending a lot of time in a barrier. Your code isn't, load balanced, not load balanced. So let me ask, what are the profilers that you guys prefer or like? There's a lot out there. I think, just tell me which ones you use. And if no one uses any, then that will be telling. Tau, okay. Okay, homegrown. Printf. Scholastica, okay. Others? I don't think I had any of those up. I said some of these. HPC toolkit, we use CrayPad a lot because we have Cray systems. Open Speed Shop, IPM, but I heard 3 different ones. So there's a lot of tools that are out there for you. I think you can find resources on how to profile your code there. Okay, and then, so the second thing we want everyone to do is to do the same thing that Chris did, is to make a map of the number of MPI tasks and OpenMP threads. Because this is really important. I mean, maybe your choice, you choose not to optimize your code, but you can at least run it at the right concurrencies, right? You can at least choose the right breakdown. You know, if Chris wanted to stop here and say, okay, I'm not going to optimize my code further, at least he would be using this point and not this point. So you've got to do, with 60 cores on a node, you really have to do that parameter sweep. It doesn't take that much time, but do that so you know you're not running here and wasting all your allocation and your time, and you can run down at the bottom. Okay, so then the second part of this is, again, to do what Chris did is to measure the efficiency of your OpenMP implementation. So if once you add 2 threads, if you all of a sudden your performance has just tanked, then you know that's where you can need to go and spend some time, is making sure your OpenMP implementation is optimal. So it goes without saying, if any one of these is not looking good on your graph, you should spend time doing that. Yeah?
Is OpenMP 4 definitely going to be the programming paradigm for the new platform? Because we need more explicit control over memory in terms of looking at the effects.
Yeah, so that's, I'm glad you brought that up. I actually just saw a presentation from Intel the other day, and so yeah, OpenMP 4 does, with the Intel compiler, gives you more control actually over what you tell it to vectorize, and we should have it. It's supposed to come out and be supported in the Intel 15 compilers, and I hope we'll have it soon on our Babbage testbed. I don't think that many. Do you have some? Oh, really? Okay. Well, it is supported in Intel programming, model. But we actually haven't had that many. Jack, do we have questions on that?
I haven't seen any users using it. We mostly have users that are already running on a variety of platforms, so it's more a question about how they migrate these codes rather than putting in a specific compute architecture.
Yeah. I think that a lot of people do want portability. We get users, right, that they don't know where their allocation is going to be any given year. They may get time on the Blue Gene at Argonne, maybe at NERSC, maybe at Oak Ridge. So that would probably pull against it. Okay, so then the third step I'd like to encourage people to do is to run your code in what we call both packed and unpacked mode. Okay, so this is a hopper node, and what I'm calling packed is when you use every single core on the node. Okay, and what I'm calling unpacked is when you only use, say, 1 core in this NUMA domain. Okay, so if you've laid out your memory correctly, your cores here should be accessing the memory that's closest to you. So if you run on a single node, here there's 24 cores. So I'm telling you to run on one case that's packed and one case that's unpacked. So you're going to have to use 6 of these nodes in order to do that. OK, so let's do a little experiment. You run this experiment. You use the same number of cores, but you have different number of nodes in the packed case and the unpacked case where you have 6. And so then the question is, if I tell you that this unpacked case where I'm using 6 nodes runs, say 5 times faster, what's your hypothesis? What could be happening here? I'll tell you the cores are exactly the same.
Is it 5 times faster per core?
Time to solution.
But you're also using 1/6 the number of cores, so we're going to...
Sorry, so I'm going to use 6 of these.
Oh, okay.
I'm going to use 6. I'm going to use 6 nodes that are unpacked. I'm going to use 1 node that is packed. And if I tell you that this unpacked case runs significantly faster, I chose 5 here. What could be happening? The cores are the same. If anything, you're going to have to do more communication across a network, because our networks are pretty fast. So what could this be telling you?
Memory contentions accommodating this.
Yeah. So maybe what's happening here is that in this packed case, these guys are all competing for memory bandwidth. And in this unpacked case, they no longer have to compete, and you'd see a speedup. Now, what if you run this unpacked case and there's no difference? What does that tell you? It would tell you maybe there's not memory contention, right? So why does this help you with an advanced architecture that has 2 levels of memory? Well, what would you do now if this unpacked case runs a lot faster and you have these 2 levels of memory on the Knight's Landing? So you think about memory placement, but you can also start to think about, hey, on this Knight's Landing processor, they've told me I have on-package high-speed memory that's 5 times the memory bandwidth. So now, you can think about, now the question is, uh-oh, did I do that? I don't know. Do you want to? And then we'll talk more. So the question is, we haven't seen this hardware yet, but how are you going to choose? You only have 16 gigabytes of fast memory. What are you going to choose to put in that fast memory? And that's a question that I think we're going to be spending the next year or 2 really looking at. So if an application has a lot of contention, memory bandwidth, you spend a lot of time doing memory access, then you may want to really think about not just using that on-package memory as a cache, but thinking about how you might allocate data into it. And so, if there's an architecture person in here, they're going to say that's a really simplistic measure, is to measure something running in packed and unpacked mode. But that's sort of the first order that you can look at. If there's no difference when you run a packed and unpacked case, then maybe you're not having a lot of memory bandwidth contention, and you can focus more on your OpenMP implementation or vectorizing your code. If you have a lot of memory bandwidth contention, then maybe working on vectorization isn't going to help you that much, because the registers are starved anyway. So there's some questions there about, and it could be in different routines. One loop, right, might not have a lot of memory bandwidth contention, another might. But that's a starting point as a way you can think about using the on-package memory. OK. So this is going to be, I think, a new challenge, is how to use this on-package memory. And I think you're going to see it in a lot of architectures coming up. OK. For vectorization, the Intel compiler has actually gotten significantly better. And so you can use this flag called vec report, and it will actually tell you which loops were vectorized, which weren't, and why they couldn't. So I think I'm running low on time, so I want to skip a little bit forward. So the next couple of slides are from John Shelf, who is in our computational research division. And so, something that John looked at is how did we used to buy computers and how are we looking at them now? And so one thing he said is, we used to look at this peak clock frequency, and now, we're really designing for power. Flops used to be a big cost. Now, data movement. It's moving data from memory back and forth. Concurrency used to have a small growth in the number of cores per year. Now you see huge growth. Memory scaling, the memory can't keep up. You have to think about locality, and before you didn't have to do that. Uniformity, you used to assume that all the cores were the same, and they are on the nice landing, but we'll see some architectures that's not the case. And then reliability, when you have all of these cores, how are you actually going to keep your program running? And so this is John's sort of idea, or what he sees coming down, the pipeline from different architecture vendors. And so what we have are a number of what are called thin, lightweight, slow cores here. But also on that same node, you could see some fat cores that might be able to help with serial parts of your code. You'll likely have on-package memory, like you're seeing in Nice Landing. But you'll still have either DRAM or there could either be flash on the node. So the challenge really, again, is how you program this. How do you program a fast core, a slow core, on-package memory that's farther away? And this actually, it gets harder and harder for the programmer. And then, this is, I found a really interesting concept is we've spent so much time in HPC worrying about and thinking about our networks. How should you architect your interconnect between nodes? But we're getting so many cores on a chip now that you have to think about the network on the chip. And so what should be the topology of the network on the chip? Should you divide it into smaller domains? And processor designers are thinking a lot about now the communication on the chip. Because you can imagine, if there's 200 cores on a node, just trying to keep these all in sync becomes a lot harder. So, okay, and then I think in summary, if you're kind of interested in this work, if you're a fourth year and you're finishing up, we're going to be launching a postdoc program to help our different application teams get ready for the Cori architecture. So our plan is for the postdocs to work with the scientists, the PIs of these different projects, but to also be able to work with folks at NERSC in our application readiness team and learn a lot about performance and architecture too. So this is the view from Berkeley Lab. I'll say it's a better view than I think any other lab. And I think what Jack and I were talking last night about the average temperature at Berkeley in the summer is going to be better than any other national lab too. So that's my promotion of Berkeley Lab and this postdoc program. So this should be announced soon, and we'd love to have a lot of applications from the CSGF community. So we have time for a couple questions. NERSC, yeah, complaints? No. Or if there's any questions. Actually, I'll be happy to take questions on NERSC or Edison or Hopper or Cori or anything. we do. Yeah. But, so, Jack, the question was, do we have a CSGF allocation? And I think we do.
Come see me after we can.
Yeah, and we also can very easily give out what we call like startup grants or awards. So, yeah, don't not do something because you don't have an allocation or time. Other questions?
So I think Carver was being dismantled soon.
Yeah, Carver is about 5 years old.
Any plans to replace that with a new sort of, what people call a normal Linux Intel system?
So we will be getting about 10 racks of Haswell compute nodes that will go into Cori. And we think of that as sort of our data partition. There'll be larger amounts of memory per node, probably different queuing structures. So that's our plan, is to transition that workload to Edison as well as to Cori. So if you have an application that, for whatever reason only runs on Carver, we think we've accommodated all of them to be able to run on Edison. But if you have an application that doesn't run well, let us know, because we want to understand that. I know it can be a little less flexible, but we've tried to add those features to the Cray systems.
With Intel moving away from the accelerator model, where do you see the future of sort of the interplay between this Manycore on node and like a GPU accelerator? I mean, is there a possibility of a machine that with Knight's Corner and
No, I was going to go back. You said Knight's Corner and a GPU? Oh, God, that sounds horrible, doesn't it? I think what you'll see is, and NVIDIA has said this publicly, right? They announced a partnership with IBM at supercomputing last year, is that the accelerators will get more tightly integrated with the main node. So we'd expect, right now, on a GPU system, you're going over a pretty slow PCIe bus to get from the compute node into the GPU. We imagine that becoming a lot high bandwidth. NVIDIA has announced that in the future years. So I think it would be more tightly coupled. I think the question I asked John, I was looking at this, was, so in this case, is there any difference between what's considered a thin core and an accelerator? And he said there was still a lot of debate about that, about what, would these be considered the same thing? So but I really hope you don't get a Knight's Corner and a GPU that sound in the same node. That sounds really hard to program. Anything else? No?